So electrical current is the flow of electric charge. And so we usually think of that as being the flow of electrons. The flow of electrons through a wire, but it can also be ions moving through a solution. So it's some charged particle that's moving. Redox reactions, oxidation reduction reactions, can generate electrical current. An example is a reaction between zinc metal and copper 2 ions. So zinc has a greater tendency to lose electrons than copper does. So a zinc atom will transfer 2 electrons to a copper ion. The zinc then becomes a dissolved ion, and that copper ion becomes a copper atom, which is deposited on the zinc surface as solid copper. And so what we observe is if we take a strip of zinc metal and stick it in a solution of copper 2 sulfate, a spontaneous reaction occurs, and we see this black, kind of crusty looking stuff growing on the zinc electrode. This black stuff is actually copper. It doesn't look shiny and coppery because of how it's depositing. But that's a spontaneous reaction. If you try to do the opposite, if you take a piece of copper metal and put it in a zinc solution, nothing happens. Because zinc more readily loses electrons than copper does. So copper's not going to give electrons to zinc, but zinc will give electrons to copper. So this one happens spontaneously. So in the beaker, we can't use any of this movement of charge, but if we separate the 2 half reactions and force electrons to travel through a wire, we can actually generate electrical current. So electrochemical cells are devices in which you have a chemical reaction that is either producing electrical current or it is being carried out by an electrical current. So a spontaneous reaction can be used to generate electrical current, or you can use electricity to cause a non-spontaneous reaction to happen. So a voltaic or galvanic cell, those are just 2 words for the same thing, is one in which electrical current is produced. So this happens spontaneously. So a battery is a type of a voltaic cell. An electrolytic cell is one that consumes electrical current to drive a non-spontaneous reaction. So electrolytic, you have to put energy into it, making a non-spontaneous reaction happen. A voltaic cell, it'll happen by itself. So let's look at that copper and zinc again. So here is a voltaic cell. So this will generate electricity because the reactions occurring are spontaneous. So on one side, we have the oxidation occurring where zinc is losing electrons and forming zinc ions. Those electrons are going to build up on this anode, on the electrode, and they're going to try to get out of there because it's negatively charged, and a negative charge repels the electrons, so they're trying to get out. So the wire is here, and the electrons will go through the wire, through the light bulb, lighting it up, and over here and into the copper electrode. Over here, we have reduction occurring. Reduction is gain of electrons. So there's copper 2 ions in the solution. The electrons come in, and they are accepted by the copper 2 ions, forming copper metal. And so that is going to happen at the surface of the electrode, and those copper atoms then are going to be deposited on the electrode. Any questions so far? So we call this the anode, and this is the cathode. So oxidation occurs at the anode, reduction occurs at the cathode. These strips of metals are called electrodes, and that's where the transfer of electrons occurs between the ion and the solid metal. So the metal is in a solution of its own ions, and that forms a half cell. So a half reaction, a half cell, and it reaches equilibrium. And the equilibrium that's going on here is between, for this one on the left, it's zinc and zinc ions. That's an equilibrium. Over here on the right, we have copper metal and copper ions in equilibrium with each other. Zinc has a greater tendency to ionize, and so its equilibrium lies further to the right. So it's got some electrons that are loose here. That causes this to have an overall negative charge and repels those electrons. The electrons are going to run this way. They're going to come over here. When we put electrons in here, what does that do to this equilibrium? It shifts it to the left, right? So it's going to shift this to the left, forming copper. By letting these electrons escape, that allows this reaction to continue going to the right. Otherwise, it would get to an equilibrium and it'll just sit there, right? But if we allow the electrons to leave, then Le Chatelier's principle says, well, if we're taking away one of the products, then the equilibrium is going to shift to the right. And as we keep taking away, it'll keep shifting. So this electrode is negative because it has extra electrons, so it's negative relative to this one. Connecting these with a wire allows the electrons to flow spontaneously from the zinc electrode to the copper electrode. This equilibrium shifts to the right, as written up here. Oxidation occurs. The electrons coming in here causes this equilibrium to shift to the left, and reduction occurs. Does that make sense? This subject of electrochemistry, I really like electrochemistry, but there's all these positive, negative, anode, cathode, oxidation, reduction things that are really, really easy to just get all screwed up. And so you really have to be able to just think it through so that you can keep it straight. So electrical current is analogous to flowing water. And so if we understand what water does, that can help us to understand what electrical current does. So water flows. You have a river or a stream, and the water's going to flow down, right? It always goes down. It never goes up. The rate of the water moving is how fast it's moving, right? So the rate of electrons flowing is like the rate of water moving. So we can think of electrical current as being like water current with the electrons moving. And the faster they move, the greater the rate of the current. So ampere, abbreviated with a capital A and often pronounced as just amp. You've probably heard that, amp, 5 amp or whatever, a 2 amp charger for your iPhone. That is a unit of electrical current. A coulomb, capital C, is a unit of electrical charge. So you can measure the charge on one electron. You could measure the charge on something that's charged. Right? So an amp is a coulomb per second. So it's a rate of electrons moving. And 1 amp or 1 coulomb per second corresponds to 6.242 times 10 to the 18th electrons per second. That's a lot of electrons. So that is electrical current. Water current is driven by differences in gravitational potential energy, right? If the beginning of the stream is high up in the mountains and the bottom of the stream is much lower, the water's going to fall down. Ooh, I should have put a picture. I saw a waterfall over spring break, and there we have the water falling through a great difference in gravitational potential energy. So that water is falling very, very quickly, right? There's a lot of force there. Electrical current is also driven by potential difference, but it's not It's not gravitational potential. It's electrical potential. So the potential difference, it's a measure of the difference in potential energy per unit of charge. So how many joules per coulomb? So that's measured with volts, and that's another unit you're probably familiar with because, what kind of batteries do you need? Well, the smoke detector was beeping last night, so I had to scrounge around and find a 9-volt battery, right? 9 volts tells me how many joules per coulomb that battery can provide. So that's the unit of potential difference. That's larger than a regular alkaline battery, which is, I think, about 1.5 volts. So note to self, replace this with my own picture. So a large potential difference corresponds to a large difference in charge between the two electrodes. So if one is highly positive and one is highly negative, that's a big difference in charge. That's a strong tendency for the electrons to flow. Just like if the beginning of the stream and the end of the stream are very different in height, the water will flow more quickly, right? Steeply descending stream bed. So that potential difference is also called the electromotive force, or EMF. It's just another term. That is the force that results in the motion of electrons. So why do the electrons move? Well, they move because there's this large difference in charge between the two electrodes. So the bigger this difference in charge, the faster the electrons are going to move. Any questions? So electric current is like a river of water, but it's a river of electrons moving. So if we look at a voltaic cell, it's going to have a potential. It's called the cell potential, capital E sub cell, also called cell EMF, because this electromotive force is just another term for electrical potential. It's the potential difference between the two electrodes in the cell. What that value is depends on the relative tendencies of the reactants to undergo oxidation and reduction. The example we looked at had zinc metal losing electrons, right? Well, if zinc is very eager to lose electrons and copper ions are very eager to get electrons, then you're going to have a big potential difference and a large cell potential. If the difference between those is very small, that would be like a very shallow river. The water's going to run slowly. It'd be a small cell potential. So we get a high positive cell potential when we've got a substance with a high tendency towards oxidation paired with a substance that has a high tendency towards reduction. This guy wants to be oxidized, this guy wants to be reduced, and so they get along very, very well, and current flows vigorously. It's also going to depend on concentrations and temperature, but we're going to put that off until next week. Today's Thursday, right? Just checking. Okay, so cell potential. Standard cell potential. So there's that little 0 again, which we've been using to represent standard. And we've talked about things in their standard states, right? So standard cell potential occurs when the concentrations of any aqueous or gaseous things are going to be standard. So concentration of 1 molar for anything that's aqueous, or a pressure of 1 atmosphere for anything that's a gas. Solids are just solids. Liquids are just liquids. They don't have a concentration. So for that cell that we've been looking at, where we've got zinc metal reacting with copper ions, the standard cell potential for that is plus 1.10 volts. If we take the zinc out and put nickel in, nickel has a lower tendency to be oxidized. And so the nickel here, that would be like lowering the beginning of the stream bed. And so we're not going to have as big of a potential difference now that the standard cell potential drops to 0.62. The copper is the same, but changing zinc to nickel, nickel is not as easily oxidized. So both of these are going to be spontaneous. A positive cell potential tells us that it is a spontaneous reaction. If we have a negative cell potential, that tells us that the forward reaction, as it's written, is not spontaneous. If the forward reaction is not spontaneous, then the reverse reaction is going to be spontaneous. Yeah. So if the cell potential is positive, then it's spontaneous. You hook that up, you connect the wire, electricity will flow, the light bulb will light up. If this has a negative cell potential, electric current will not flow spontaneously. That's like the end of the river being higher in elevation than the beginning. Water's not going to flow forward, right? Water does not flow uphill. It just doesn't, right? And electrons do not voluntarily move uphill either. So if this is negative, it's not going to happen. Yeah. Yeah, then the reverse reaction would be spontaneous. It would want to go the opposite direction. Okay, so here are some of the words we've been using and some little hints to help us remember the associations between them. So oxidation occurs at the anode. Reduction occurs at the cathode. That can be kind of hard to remember. So oxidation and anode both start with vowels. Those two words go together, oxidation and anode. Reduction and cathode starts with those start with consonants, or you could think about a red cat, right? Reduction at the cathode, a red cat. The anode is more negatively charged, and we can remember this by remembering that anions are negative. So the anode is negative. The cathode is positive, cations are positive, the cathode is positive. Electrons are going to flow from the anode to the cathode because the anode is negative and electrons are negative, and so they are repelled by the negative electrode. They're going to flow towards the cathode, which is positive, because they're attracted to the positive charge. If we remember oil rig, oxidation is loss of electrons, right? Oxidation occurs at the anode. That means at the anode, electrons are being lost. They're leaving the anode. Reduction is gain of electrons. At the cathode, we have reduction. We have electrons coming in, and so the cathode's positive. Okay, so yeah, work on those. Flashcards might be a good idea. Any questions?
I just remember that cats, I like them.
Yes.
Cats are a positive thing.
Yeah. I like cats as well, and so I have positive feelings towards cats, and that's how I tell my students to remember that cations are positive. Yeah. So if we had electrons flowing from the anode to the cathode, and then at the cathode they are reducing something, we'd get a buildup of charge. That charge would build up in the solution. We have these electrons coming in, and so we're going to get a buildup of negative ions in the solution. We're going to get a buildup of positive ions in the other solution. And so that's not going to work very well. So we need to allow those ions to move as well. And what's often done is we use a salt bridge. So this is a bridge between the two solutions that allows ions to move without letting the solutions just mix. Because if we let the solutions mix, then we can't get the electricity. The reaction will occur just fine, but we can't get anything useful out of it. So often this looks like an inverted U-shaped tube, and it's got a strong electrolyte in it, usually something that's not reactive, maybe like potassium nitrate or something. And that'll be in a gel, and then we'll have porous caps at each end, because otherwise you don't want solutions just mixing and falling out. So the negative ions in the salt bridge are going to flow to neutralize the accumulation of positive charge at the anode, and the positive ions are going to flow in the other direction to neutralize negative charge at the cathode. So that's the salt bridge here. This one has potassium nitrate in it. So the electrons are moving this way. When this loses electrons, it forms cations in solution, right? So the cations in solution are going to cause a buildup of positive charge. That's going to attract the negative ions from the salt bridge. So they're going to come over here, and then we're going to have a neutral situation again. Over here, the electrons coming in are reducing the copper ions, and so then we're getting a deficiency in the copper ions, the cations. Can you have a solution of just copper 2 plus ions? No. There must be an anion in there, right? This thing doesn't say, the picture doesn't say what that is. It's probably something like nitrate, because nitrate compounds are soluble. So this is probably something like copper nitrate, possibly copper sulfate. There are counter ions in there, because how do you make the solution? You take an ionic compound and you dissolve it. We don't show the anion in any of the reactions because it's a spectator, it's not participating, but it is there. So if we're using up all the cations, then those negative ions that were there are left, and we've got a buildup of negative charge. That attracts the positive ions from the salt bridge. They're going to come over and hang out with those negative ions to equalize the charge. Does that make sense? Yeah.
How do you know what compound to put into the salt bridge?
That's a good question. How do you know what compound to put in there? It actually doesn't really matter. You want a soluble ionic compound and something that's not going to react instead of the things that you're intending to react.
So is potassium nitrate a common one?
Potassium nitrate is very common, yeah. It's soluble and it doesn't react very much. But there's, you could do lots of other things. You could use sodium chloride, probably. Yeah. Any other questions? So we have a shorthand notation for representing electrochemical cells. It's a line notation or a cell diagram. And as you can imagine, like drawing that whole cell out would get really tedious, right? So this is a very abbreviated form and relatively easy to type into a computer. So on the left, we have the oxidation half reaction. Is that the anode side or the cathode side? The anode side, because oxidation and anode start with vowels. So this is the anode side, and so here's the electrode, zinc solid, and then there's a line here, and here's the zinc ion, and that's aqueous. So this single line separates these two species because they're different states. This one's a solid, and this one's dissolved ions. Then we've got a double line in the middle that represents the salt bridge. So we have the one side of the cell, and this is the other side of the cell. On this side, we have copper 2 plus ions that are aqueous, and a line separating them from the electrode, which is copper solid copper. So the reactions that are occurring there, we've got Cu2 plus 2 electrons going to copper, and over here we have zinc going to zinc 2 plus 2 electrons. So the order here represents reactant to product for the reaction occurring here, and this is reactant to product for the reaction occurring on that side. In this example, these are in different states, but sometimes they are in the same state. They may be both aqueous. Then instead of a line, we'd separate them with commas. If all of the principal species in a half cell are aqueous, we have to have something solid in there for the electron transfer to occur at. In this case, copper works really well because it's a solid. But if we were going from copper 2+ to copper 1+, there'd be no solid to attach a wire to, right? So then we have to put something in there. So then we'd use an inert metal such as platinum. And so you stick a platinum electrode in there so that there's a surface. Yeah?
For the double lines that you put there, is that just supposed to be like that? What is that?
So the double line here represents the salt bridge. Yeah. So we've got the oxidation half reaction on the left, the reduction on the right, with a double vertical line, the salt bridge in between. So let's look at an example here. Here's a chemical equation, chemical redox equation. And in order to write the line notation describing that cell, we have to be able to look at the two half reactions. So there's going to be oxidation and there's going to be reduction. So sometimes you can look at it and tell what's being oxidized or reduced. Other times you have to get out your formal charges, not formal charges, your oxidation states to figure it out. But here we've got iron going to iron 2+. Is that oxidation or reduction? That's oxidation. So our oxidation half reaction is going to include 3 Fe solid. That's not 3, that's a 5. Five Fe solid going to 5 iron 2 ions. And what else is going to be in there? Some electrons, right? So we had 5 of these things happening, and each of them is losing 2 electrons, so that's probably releasing 10 electrons. That would balance the charge. The reduction then is going to have the permanganate ion. And these hydrogen ions were not needed in the oxidation reaction, so they're probably involved in the reduction reaction. So 16 hydrogen ions. And that's going to make, we'll write down the things, oops, we're going to need some electrons over there. Leave a space. 2 manganese, 2, and 8 H2O. Now, if this is properly balanced, then this should be 10 electrons here, but let's just double check. So we have 2 times 2, we've got plus 4 on this side, and we've got 16 and 2 more, 14. Did I do that right? Two, 14, and 4. Yeah, sorry. Anyway, 10 electrons. This is oxidation, we're losing electrons. This is reduction, we're gaining electrons. So writing the line notation or diagram for this cell, we've got solid iron going to Fe2+, aqueous. So this is what's being oxidized, and this is our product. So we've got FeS and Fe2+, aqueous. Those are different states, different phases, and so we put a line between them. So this is the oxidation half reaction, or oxidation half cell. Then this is our salt bridge. And then over here, we've got permanganate and hydrogen ion and manganese ion. We're not going to include water because this is all aqueous. What does aqueous mean? Dissolved in water. The water's there anyway, so if there's more or less, we don't really care. Since these are all aqueous, they're separated with commas instead of vertical lines. And we're going to put platinum in here. You could put something else in there, but platinum's what we usually choose because we need a solid electrode. And so then here's our vertical line separating those guys from the platinum. Any questions? Yeah.
How do you know where the hydrogen goes?
How do you know where the hydrogen goes? That's a good question. When I did this, Fe to Fe2 plus, I can balance this without using any hydrogens. So the hydrogen doesn't belong up here. Down here, when I write out the rest of it, I find that the hydrogens do belong there because it's all balanced nicely. So if you were starting out with just permanganate ion and manganese 2 plus, you'd be doing that half reaction balancing method where we balance all the elements besides oxygen and hydrogen, then the hydrogen and the oxygen, and then you take care of the charges with the electrons. Any other questions? Yeah.
What is solid platinum again?
Solid platinum is the electrode. Because we have to have a wire connecting this, and you have to hook the wire to something, right? Or you could just stick the wire into the solution, but then the wire has become your electrode, which might be fine, but it's still in there. There's got to be something solid for this to occur at. Any other questions? What does it have different?
The amount of electrons on each side.
You mean like this? On this one?
No, on the slide before. Instead of 10 and 10,
Mm-hmm.
there's 2 and 5. I don't know if that matters.
That's because they reduced each of the half reactions. So what I wrote here was just pulling this thing apart. If I divided this by 5 and by 5 and by 5, I get 2. And if I divided all of these by 2, I get 5. And so here is an illustration of that cell. So over here, the anode is iron. Oxidation is occurring at the anode. The iron is being oxidized to Fe2 plus. Over here, stupid pointer. Over here is the cathode. Reduction is occurring over here. Permanganate ion is being reduced to manganese 2 plus ion. There's no solid in there, and so we've got the platinum electrode here. The platinum electrode, the platinum is not reacting at all. It is just a place for electrons to come in. So we've got the wire, the electrons come in, they need to enter the solution somehow. They don't jump well. And then we've got our salt bridge with potassium ions going one direction and nitrate ions going the other direction. Any questions?